Hello, I'm Umnik. I will be solving the first round 1063 and I'll try to explain what I'm doing on the way. Okay, problem A. Souvlaki versus Kalamaki. Okay, two players, Souvlaki and Kalamaki, are given a sequence A of n integers. They will play a game that consists of n-1 rounds, which are numbered from 1 to n-1. Souvlaki plays on odd numbered rounds and Kalamaki on even numbered rounds. On the each round, a player can choose to take exactly one of the following actions: skip his turn and proceed to round I+1, or finish the game if round I was the last one, or swap elements AI and AI+1. Okay, so they're like moving left to right and can choose to swap two elements they're looking at right now. Okay. Souvlaki wins if after the end of the last round, A is sorted in non-decreasing order. That sounds very hard to achieve. However, Souvlaki does not like losing, so before the start of the game, he may reorder the elements of A in any way he wants. Is it possible for him to do so such that he has a guaranteed winning strategy? And N is at least 3. So okay, basically if the person who doesn't want it to be sorted, if they can like swap two elements that are not equal, then they always win, right? Because they can just put the larger element first and then they will move on to the right. So there will be, so let's say we have like x and y, and x is smaller than y. And then that second person can put y on the position I and x on position I+1. And after that, element y will always stay on position I, and element x will be somewhere on the right. So the array is not sorted in the end. It just cannot be like the for certain will be elements y and x that are sorted in incorrect order. So the only way the first person can win if the second person like at every their move, the two elements they're looking at are equal. But then I think it's true that like we just want to sort the array at the beginning, like before the game, and then just check that it is true that the two elements are equal, because like in the end the array should be sorted. There is only one way to sort the array in non-decreasing order. And basically they need to make sure that no swaps happen, or like no reasonable swaps happen. So opponent can swap two elements if they're equal. That doesn't matter, but like otherwise, like we don't need to swap anything like in the game, because we can decide the order before that. So the solution is to just like sort the array and check that the second player will always look at two equal elements. If that is true, then the answer is yes, otherwise it is no. Okay. How I'm talking about it might look like I'm saying that this problem is dumb, but like pretty much every second division problem A is dumb, and this is a smart dumb problem. Like the solution is like very simple, but it's not obvious that the solution will be that simple. So like yeah, for me, like while I'm reading the statement, and since I'm reading it out loud, like it takes time, like when I'm done with reading the statement, I already have the idea of like what the solution should be, but then I'm talking through it like for you for the video, and like for me the act of talking through it, like it doesn't add anything to the problem because it's so easy, and like I feel like the problem is too easy for me to talk through it, and like I'm kind of resenting it at the moment. Uh, but yeah, it's a nice problem actually. Like, for a second division problem A, this is a nice problem. It is not super easy, but it is easy enough. That's a tough line to walk. Okay, so I read the array, I sorted the array, now I need to check that the elements at which the second player will look are always equal. So in zero indexation, it is like the first element is an odd position and the second is an even position, so I'm iterating through odd positions. Here like it is smaller than n minus 1 because like I will be looking at position I and I plus 1, and I plus 1 should still be in the array, so it should be smaller than. So I guess like the more reasonable way to write it would be like this. The second element I'm looking at is still in the array. If they're not equal, then the second player will win, and therefore we return false. Problem B, what are those names? What is this language? Sigatakimata? I don't know. Thankfully the statement is in English. You're given a permutation P of every integer from 1 to n. You also own a binary string S of size n where Si is 0 for all I from 1 to n. What an interesting binary string. You may do the following operation at most 5 times. Choose any two integers L and R such that L is not greater than R, so we're choosing a segment. Then for every I such that I is strictly between L and R, and element pi is strictly between two elements, like on the ends of the segment. So yeah, we're looking at PL and PR. Those are the elements on positions L and R in our permutation. And then, so minimum of them is like the smaller, maximum is bigger, and PI should be between them, strictly. Okay. So for every I such that the index is on the segment and also the value is on the segment between endpoint values, you will set Si to 1. Okay. You're also given a binary string x of size n. After performing operations, it must hold for every I that if xi is 1, then si is 1. Note that if xi is 0, then si can have any value. Okay, so we have some positions that we have to set to 1. We might set some other positions to 1, that's fine. But like those that are set to 1 in x, we have to set to 1 in s. Figure out any sequence of at most 5 operations such that the aforementioned condition is satisfied, or report that it is impossible to do so. Note that you do not have to minimize the number of operations you make. It sounds very weird. For each test case, if it is impossible, output -1, otherwise output an integer from 0 to 5 the number of operations, and then the k operations. Yay, A is accepted. Okay, so problem B sounds weird. Okay, so we have some permutation. Actually, like when we're talking about like this thing of like looking at the position such that the position is on the segment, but also the value is on the segment between border values, I think it might be useful to look at it on a two-dimensional plane. So here we will put index and here we will put elements. And so like our permutation is a sequence of points on this plane. So for every index, like it has some value, so we find that value here and say that, okay, so if we have value pi on position I, like we will have the corresponding point with coordinates I and pi. And our permutation will be like a set of n points on this plane. And like we have every I coordinate from 1 to n exactly once, and every pi coordinate from 1 to n exactly once. Something like this. Then the operation we were talking about is we're choosing two indices, let's say this one and this one. And we are looking at the elements such that their index is between those two and the value is between those two. But that actually means that we're looking at the points that are inside this rectangle, like strictly inside. So we're choosing like two pivot points, build a rectangle on them, and then for all the points that are inside this rectangle, we assign 1 to those points. So we are given a string that we want to achieve, but we are not given any limitations on that string. So like it feels like there are obviously points that we cannot set to 1. For example, we cannot set the leftmost point to 1, right? Because like to set someone to 1, we need to choose 2 points like on the other sides of it, like by every coordinate, but there are no points on the left, right? So like for this one we cannot set it to 1, for the lowest, for the highest, and for the rightmost. Those we cannot set to 1. So probably, like by how the problem looks like, probably we can set everything else to 1. So is it just like taking this rectangle, and the opposite ones, like this and like this. Oh no, look, we have this zone that is not covered yet, but we have one more query. Probably just taking those 2 points should cover it always. Yeah, that seems reasonable, right? So we will have those 4 points. Like some of them can be the same point, which like you need to think about. But I think it should be fine. We just like don't print those rectangles because they will be empty, and that is fine. Also, I think it is allowed to choose L and R that are the same, right? Yeah, L and R can be the same. Okay, so like in general, we will have like those 4 points in some configuration. This configuration is a bit different to what we have had here. Some of the points can coincide, but like we know that all the other points are strictly inside the square, and then like choosing leftmost and rightmost point will cover everything that is between them by value. And then like to cover the upper part we are taking this rectangle and this rectangle. And to cover the lower part we will take this rectangle and this rectangle. Yeah, that looks correct to me. Okay, that is a hard problem. Why would you put it on position B in second division? I mean, like, I guess it is guessable, but yeah. That seems like a incorrect decision from coordinator, I guess. I don't know. Well, I'm assuming they had testers, so probably it tested like an easy problem. Okay. So I'm finding the position of maximum and minimum, and then I'm just printing 1n, one position of maximum, one position of minimum, position of maximum n, and position of minimum n. And that will cover everything except those 4 points. So if any of those 4 points have ones in the string, in the binary string we are given, then it is impossible. Otherwise, we will cover everything that is possible, including those bits that we have to. Okay, great. And then permutation, and then the binary string. Okay, sure. And maximum, minimum are actually just 1 and n, because it's permutation. I'm reading the permutation, finding the positions of 1 and n. So now my interesting positions are 1, n, pq, or pq, I guess. Okay, then I read the string. Yeah, when I said 1 and PQ are in 0 indexation and 1 and N are in 1 indexation. That's bad. I need to think in 0 indexation, but print them in 1 indexation, obviously. Okay, so if any of the important positions are ones, then it is impossible join. Otherwise, I will always do 5 operations. I am allowed to do the same operation several times, which is like stupid. I am allowed to do operations with equal indices, so that's also fine. So what were my operations? Yeah, I put 1 and n the variables because like I'm not sure what will happen if I try to do printf with a constant. Like this should take variable. I'm not sure what will happen here. So I will just have like xy pq and we have an xy xp xq py qy, and that's it. Okay, so the minus ones are at correct positions, and other than that I don't want to check it, but like it should be correct. Okay, problem C, monopathy. You're given a grid A of 2 rows and n columns, where every cell has value from 1 to n. Let f of Lr, where Lr between 1 and 2n, and L is not greater than R, represent a binary grid B of 2 rows and n columns such that Bij is 1 if and only if Aij is between L and R. Note that cell ij denotes the cell I rows from the top and j columns from the left. Okay, so like we have a grid of numbers and then we can transform it to the binary grid by saying like the numbers in this segment are ones and the numbers outside of that segment are zeros. Now count the number of pairs of integers LR such that they are valid. And in f of LR there exists a downright pass of adjacent cells with value of 1 from cell 1 1 to n. Downright pass. So a downright pass of adjacent cells is a sequence of cells such that each cell in the sequence shares either its top side or its left side with a side of the previous cell in the sequence. So, like, moving in the only in down or right direction. Okay, interesting. So, like, obviously, we need to include the starting value and the ending value in our segment. So we have like some basic segment, and then we can like enlarge it to the left and enlarge it to the right by taking more values. All correct submissions for problem B have been rejudged due to a mistake in the checker. Wow. So the rejudging accepted submissions half an hour into the competition. That's unorthodox. Okay. Well, it doesn't matter for me, but it's unorthodox. Okay, back to problem C. Right, what was I saying? We have some base segment, we can enlarge it. Enlarging the segment is obviously better. We're making more cells to be ones, like ones are kind of possible cells. So there is more chance that the pass will exist. Which means that like for every left border there will be like a right border such that it is a minimal right border to make it good pair, and like when we move left border to the right, that smallest right border will also move to the right. Basically, we can do 2 pointers. And like doing 2 pointers would be a solution if we know like how to check that like this particular segment is good. So what do we need to do 2 pointers? Well, we kind of need to like be able to change the values in our binary table and check that a path exists. But that's kind of easy, right? Because our grid is just 2 rows and n columns. Like the path always looks like we're going to the right up to some points and moving down and then right like to the end. So we can just maintain like what is the farthest point to the right we can move from the start in the top row, and what is the farthest point to the left we can move in the lower row. And we just need to check that like those two segments intersect. If they don't, then it means that there is no path. If they do intersect, we can like, take any column in the intersection and go to it from the start, then go down in that column, and then go right to the finish. So yeah, if it wasn't two rows, I wouldn't know how to solve this problem. But it is two rows, and probably because like otherwise the problem would be like uh, at least much harder, if not unsolvable. So no, probably still solvable with three columns. With four, it's much harder. uh, Not columns, rows. But yeah, okay. So we're just doing two pointers. Doesn't even matter. Um, like I don't need to find the basic. Just do two pointers. Like have left border, right border. We move right border to the right until we either reach the end of all possible values or we arrive at a situation which is good. Good means that the path that we want exists. And then, uh, if we arrive at a situation that is good, then we could have moved the right border further to the right, so we just add the number of valid positions on the right to the answer, and then we moved left border by one. Some values will become zeros from ones. Maybe it breaks the property that we want, and we will have to move that right border further. The total number of moves will be linear, and also, despite the fact that we can have the same values in the table, it's easy to see that for every value, like at some point, the right border will reach it, and we will like change it in binary table from 0 to 1, and then the left border will move over it, and we will change it back from 1 to 0, and that's it. So every value changes only two times, so the total number of operations will be linear. And like, how do I find those like rightmost point which I can reach in the top row and the leftmost point which I can reach in the bottom row? That's just like the first and the last zero in my binary table, so I can just like maintain a set of all zeros in the top row, maintain a set of all zeros in the bottom row, and like be able to take the smallest of them, the largest of them, and do all the checks I need to do. That is n log n with kind of a big constant. So n is like 200,000, but we have like 2n actually cells. Each cell changes its value twice. So it's 4n operations to the sets. 2 seconds. I think it should be fine, but it is like a bit scary. Uh, it is a lot. Probably can move the logarithm like So now I have like 2 pointers, which makes it of n operations, but I need sets because I'm like adding and removing zeros. But if I were only to add zeros, then it would be easier to maintain minimum and maximum. Just like update with the new value, update minimum, update maximum with the new value. So I probably could, like instead of doing 2 pointers, which requires sets, I could do like some divide and conquer, which would be like n log n operations, but those operations are fast now. So that would be that would have much better constant factor. But I think n log n with sets should also be okay. It is a bit scary. But yeah, I just want to write it with sets, I guess. So to implement that, I would need like for every value all the cells with that value. So like when I change the availability of that value, I know what cells change. Um, Okay, so I'm reading the table. On position ij, I have number x, and so I'm saying for the number x in the row I, there is an occurrence on position j. Okay, and now I will be doing my 2 pointers. So R points at the first number that is not added yet, and so while not is good, I want to turn on that value and then increase R. But also I might like run out of the values. Just like if I reach L such that for this left border, even if I move R to the like to N to the maximum value, it is still bad. And so while R is at most to N and this is happening, I'm doing it. And like if not is good, even after I finished, it means that I run out of values to add, and this L is already bad, and all the further L's will just be even worse, so I'm just breaking. And here I need to add the number of valid R's to the right of my current value. I think it should be like +2 minus R. If R is 2n plus 1, it means that I have reached the end, but it is good right now. So like that value is good, but there are no further values of R valid. So this value should be 1. If R is 2n plus 1, then this should be 1, which is correct. So this should be what I need to add. And here I turn off L by I'm moving my left border by 1 to the right, so those values are turning off right now. They're not inside the segment anymore. And after I did all that, just printing the answer. So to turn on number X, I will run through all the positions on which there was number X, and so my set stores the set of 0 values. So when I turn them on, which means like from 0 to 1, I need to remove them from the set. When I turn something off, I need to do the opposite. I need to add them to the sets. That means that before I do everything, all my like Boolean values in the second table are zeros, so I need to insert all of them at the start. Also, I guess for simplicity, let's let's write the check function bool is good, and we will see like what other things we can do to make it simpler to avoid some corner cases. So what should happen here? I need to find what is in the upper row, what is the rightmost position I can reach, which is done by taking like the first 0 in the upper row. So let's say that X is up begin. Similarly, in the lower row, we take the maximum 0, want to find the leftmost position which I can reach, and to the left of it, like it stops when we encounter the first zero when we go from right to left, so it is the maximum position. And that would be like rbegin, but I don't like to use those. I'm not sure how that works. So I would write pref of down end. And so like x is first zero in the top row, y is last zero in the bottom row. It is good if like in between them we have a channel to pass from the upper row to a lower row. So good means that x minus 1 is strictly greater than y. So x is impossible on the top row, y is impossible on the lower row. So x minus 1 is the rightmost position we can reach in the top row, and it should be strictly to the right of y, so that like when we go down we can go to the right. Okay, that like how this function should look, but there can be like a bad case when we don't have any zeros, right? So like in, for example, in up or down, we don't have any zeros, and then like this operation of what's the word like taking the value by the iterator, like it is illegal. This iterator is not a like iterator to a valid element. What should I do in this case? Well, I should take the I should take some dummy value saying that like it is after all the elements, so it should be like n here. I can do it like that. I can say like if up is empty, return n, otherwise take the first element. That would be correct. But the better way, in my head at least, is to say, okay, let's just insert n here. And so like when I don't have real elements, I will just take n, because n will always stay there. I cannot remove it. This cannot happen for like p equal to n. So if all the actual positions are turned on, I will take the dummy positions that I inserted in the set beforehand, specifically for that reason. And similarly for down, if it is empty, I should take like the position to the left of the leftmost possible position, which should be -1. So let's just insert -1 here. I'm a bit worried about time limit potentially, but let's see. Okay, we will read problem D1 right now. D1 diadrash. This is the easy version of the problem. The difference between the versions is that in this version you can make at most maximum of 300 and n divided by 2 rounded up plus 2 queries. You can hack only if you solve all versions of this problem. And what is in the second version? You can make at most 30 queries. That's a big jump. Okay, it's under 1 second even. Time limit was 2 seconds, right? So like it's less than time limit divided by 3, which is good. Okay. This problem is interactive. There is permutation p of the integers from 0 to n minus 1 hidden from you, Additionally, you are given Q ranges. Okay. You need to discover the maximum max among the values of P in the Q ranges that are given to you in the input. So like for the Q ranges we are given, we calculate max for each one of them, and we need to calculate maximum of those values. Okay, it is set in the next sentence. Formally, you must discover the value of maximum of max of like this subsegment of permutation over I from 1 to k. Yeah. To do so, you may make at most that number of queries of the following form. Choose any two integers, choose any segment, and you will receive the value of max on this segment. Okay, and this is a permutation. So max on the permutation is like pretty simple because like each value can appear only once. So basically max of the subsegment is minimum over like the values that are outside of that subsegment and n. Like if you take the whole array and the max is n, otherwise like you have removed some values from the prefix and suffix, and like the minimal excluded value is the minimum over the values you excluded. So those values on the prefix and suffix. Those are the ones you excluded, so you take minimum over them. Kind of like by definition of max, but like it works exactly because each element appears only once, so if you exclude it once, it's excluded now. Okay, you don't have any more occurrences of that element. Okay, so n is at least 4. Interesting. And up to 10,000, and Q is very big. Additional constraint, it is guaranteed that no range is repeated in the same test case. So like among the Q ranges we are given, they are all different. How is that important? Couldn't they just like, what? Okay, it doesn't seem important. Maybe it's like for some ease of implementation, I don't know. But like, that doesn't seem to do anything. Alright, we have an easy version and a hard version. In hard version we can make at most 30 queries. And the limitations on n and q are the same. But here we can do maximum of 300 and n over 2 rounded up plus 2 queries. Okay. Okay. Well, like I will, like I'm kind of in the mindset of trying to solve the hard version, but like I don't know yet. I need to understand something about the problem, like what information I can get from queries, and then we'll see like what solutions I can come up with. Like my maximum goal is to come up with a solution like under 30 queries. So let's write it down somewhere. So we have easy and hard subtasks. Hard is 30 queries, and easy is either 300 or n over 2 rounded up plus 2. Whichever I whichever I fit in is already good. Okay. And up to 10,000, Q up to a lot, 300,000. So okay, like this 30 looks like two logarithms, right? Look, log n is like at most 14. So 30 is kind of two logarithms plus 2. Interesting that plus 2 is here. Okay. We have permutation. We have some ranges that are given to us. On each such range we calculate max, and we want to find maximum of those maxes. Okay, so I have drawn it like this because like we can tell right away that of those like potentially 300,000 segments over which we're taking maximum, like we only need at most n. Why is that? Because I can just forget about segments that lie like inside other segments. If you take a segment and then like increase its borders, its max can only increase, and then we're taking maximum. So the max of this segment is surely not less than max of this or this segment. So we can just forget about them, and we can just like for every left border we can leave just the maximum right border among the ones present, and also for every right border is maximum left border that is present. Basically, we can remove the segments that lie inside other segments, and then we will have like the sequence of queries that is like if we sort them by left border, they will be also sorted by the right border. Something like this. Okay, the next thing I said is that if we want to calculate max on some segment, there is a prefix that we removed, there is a suffix that we removed. We can calculate minimums on this prefix and this suffix, and that minimum is the max on the subsegment between those prefix and suffix. And this actually looks already pretty good to me. Look, what will happen when we are looking at different prefixes? Look, the more we take in the prefix, the smaller the minimum will be. So like when we increase the left border, we increase minimum on prefix. Not increase, decrease minimum on prefix. It's here. Decrease minimum on prefix. For the suffix, well, it's kind of similar, but now like increasing the right border is removing the elements from the suffix. So we're making the suffix smaller. So when we're increasing the right border, we're increasing minimum on suffix. But not that like after we did this simplification, when we look at those, like at our query segments, if they're sorted by left border, they're also sorted by the right border. So let's look at the query segments. Let's order them from left to right by left border, but it will be also ordering from left to right by right border. So we can order them. We have like okay, I guess I wrote the index to the left here and under here, but like to the left makes more sense. So let's say I ordered from 0 to k. And again, we will look at it graphically. So we have our queries. So it's query ID kind of. And here we want to look at the like max value, but what we will actually look at are prefix minimums and suffix minimums. And actual max value will be the minimum of the corresponding prefix minimum and suffix minimum. So when we move through the queries by ID, but by ID means left to right, both by left border and right border. What we wrote, like left border increases, it means that the minimum on prefix decreases. Let's say that this is yellow, and like we start at some high value, and then it goes down slowly. Maybe not slowly, I don't know. So it will be some like decreasing function. Actually, it will, well, I don't know. I want to say it will reach 0, but maybe it won't. It can stay like on the same level for a long time, but like it cannot go up. Now for the suffix, let's say it's blue. Again, we increase in the right border, but that means that the suffix minimum will increase. So it starts at some low value and then slowly move up. Something like this. And what will be the actual max? Well, I said that max is minimum of those two values. So like on this graph, like at every point, we're just choosing the smaller of two values. And so the graph will look like this. And we are interested in the maximum. Well, maximum will be here in this particular case. But like what is important about that point is that it is where our prefix mean and suffix mean lines intersect. There will be like at most one point where they intersect. Why is that? Well, because so the prefix minimum function decreases, the suffix minimum function increases, so they kind of like have this X shape. So they will have one intersection, and when we are taking minimum, like before the intersection, it will be the like the suffix minimum will be the smaller value, but after the intersection, the prefix minimum will be the smaller value. So like here's the intersection. So before that we're looking at the suffix minimum. After that we're looking at the prefix minimum, and like well, clearly, so before the intersection, it will increase because it behaves like suffix minimum, which increases, and then after the intersection, it will decrease. So the maximum value will be near the intersection. Like our functions are like kind of discrete, so the intersection can happen at like non-integer values. So we need to look at the closest integer values to the left and to the right. Okay, great. So what is like potential solution for us? We want to find where this intersection happens, and then check up like the leftmost, the closest to the left and closest to the right options. So check the closest to the left and closest to the right options are like those +2 that we have for hard version. So for hard version, we want to fit into like this number of queries. Those are the +2. And to logarithms, well, it's an interactive problem, which means it's a binary search. And well, yeah. How do I understand if we are to the left or to the right of the intersection point? Well, on the left of the intersection point, suffix minimum is smaller than prefix minimum. To the right of the intersection point, it is vice versa. So if we like choose some point, we want to look at the suffix minimum, we want to look at the prefix minimum and compare them. If prefix minimum is bigger, then we are still on the left of the intersection point. If prefix minimum is smaller, then we are on the right. Need to be kind of careful with the equal values, but well, first of all, that shouldn't happen because we have a permutation. Well, unless we have like, I don't know, if I have just one segment that coincides with the whole array, I would say that both prefix and suffix values are kind of n, so they're equal. But other than that, we wouldn't have equal values for queries. And yeah, we are not allowed to ask like prefix min and suffix min values, but we can ask max. And we already said that like max on a segment is minimum of those two. Well, let's just make, if we want to find minimum on a prefix, let's just make the suffix empty. So we will ask max on the suffix, not including this prefix, which is equal to the minimum on this prefix, and like vice versa for the suffix. So to make one iteration of binary search, we need to spend 2 queries. One to ask for prefix minimum, one to ask for suffix minimum, and this is the number of iterations of binary search we need. So we will spend exactly this number of queries. Great. Input multiple test cases, NQ, and then segments. Okay. Okay, so the first thing we need to do is to trim those queries and achieve that situation when basically we removed all the queries that lie inside other queries. That's probably the reason why they made sure that there are no equal segments, but it's not very hard to handle, but it is slightly easier without them. Okay. So yeah, we want to remove all the queries that lie inside some bigger queries and have our queries sorted by the left border and they will be sorted by the right border automatically after that. Okay, cool. What is it? Yeah, so I just want to. There are several ways to do that. The one I prefer is let's sort our segments by left border, and then we will go through them and while the sorted by left border and by right border it is fine. How it can break. It can break if we add the next segment and its right border is smaller than of the previous segment, then it means that our new segment just lies inside the old one and we can safely ignore it. Or it could have a bigger right border but the same left border as the previous segment, which would mean that the previous segment lies inside our new one. But in that case, we can ignore the previous segment and just keep the new one. So we'll sort our segments. And basically, the segments we have will be, kind of in a stack, but we will not remove more than one at a time. It is kind of similar to how you would do convex hull and stuff like that. But we will not remove more than one at a time, so it doesn't even matter that much that it is a stack. But I will basically I will reuse the same vector. I will go left to right, and the already processed prefix of my segments will contain the stack of currently active segments, and since I cannot have more segments that I processed, so it is fine. I will not try to rewrite the segments that I have not seen yet. Okay, you will see how it works. So this is the size of my current stack, kind of. Okay, so I think that's it. How does it work? So I'm going through the segments left to right. If I don't have any segments on the stack, then I just put my on top of the stack. And the other case when I just add it without removing anything is if I should put it in the brackets. I mean, it has, I think, and has higher precedence than or, but I don't want to rely on that. So if if it is correctly sorted, basically, if the left border is strictly greater than the left border of the previous segment and the right border is strictly greater than the right border, then it is good, I just add it. Otherwise, so I know that I have something on my stack. I look at the topmost and I know that they're not sorted like correctly, like this. So what are the options? How can they be sorted incorrectly? So either the new one lies inside the old one. I know that by left border they're sorted like this because I sorted them by the left border. And so if the right border is not bigger than the right border of the previous, no, the segment on the top, that means that the new segment is not needed. It fully lies inside the old one. So in this case, I just do nothing, which means don't change the stack, just move to the next possible segment. But if that doesn't happen, and also this didn't happen, which means that they're not sorted correctly, it means that this should have been broken, and like it is broken if and only if those left borders are the same, because they're sorted by the left border. So the left borders are the same, but this is not true. So my new segment has strictly greater right border than the one on top of the stack, which means that the one on top of the stack is not needed. It fully lies inside the new one, so I just replace it with the new one. Like normally with those like stack-based type algorithms, like there should be like a while that removes from top of the stack while they're not needed because they're fully dominated by the new one. But in this particular case, like more than one cannot be removed because I know that like for the segments on my stack, they all have different left borders. Like that's one of the conditions that should happen for them to be on the stack. So they all have different left borders. They're sorted by that left border, and like the ordering by the right border is the same and also strict. And I know that my new segment also have like not less than that one by left border. So the only segment on the stack that can be inside my new one is the last one. All the previous ones, like their left border is strictly less than the new one, so like, we can't remove more than one. Okay, now just size, well, a size. So, I mean, not needed technically, but whatever. Okay, so now I have my size possible segments that like can be maximal because they're like maximal by inclusion. There is no other segments that contains them. We can like, assert that size is at most n. Okay, now I want to do a binary search on those. Basically, remember, yeah, like those are my potential segments. I have two functions on the segments, like prefix minimum before that segment and suffix minimum after that segment. I know about those functions that they behave like this. I want to find the intersection point, and I do this by doing binary search. So I will say that my current left and right pointers are like before the array and after the array, and I want to make them next to each other, and the left one is where prefix maximum is still greater minimum. Prefix minimum is still greater than suffix minimum, and in the right one, prefix minimum is already smaller than suffix minimum. So if query, I want to compare prefix minimum and suffix minimum. To take prefix minimum, I need to query max of like the corresponding suffix, which means it is like ak first and. So this is max on the suffix, which is the same as minimum on the prefix. So this I compare with suffix minimum, which is prefix max, prefix up to the right border of my segment. And how do I compare them? If the first one is bigger than the second one, it means that I'm still to the left of the intersection point, so L is K, otherwise R is K. Okay, great. And now, actually, like I found the intersection point, so L is pointer to the like closest to the left of the intersection point query segment, and R is pointer to the closest to the right. So I just query them, and one of them is the maximum max. So I just say that ans is 0, and I want to query left and right, but one of them may not exist. Like if the intersection basically happened, like for example, to the left of the leftmost segment, so like all the prefix minimums are smaller than the suffix minimums, it means that like my imaginary intersection is like to the left of all my segments, and L will be -1 in that case. So I don't have left option, but if I do have left option, I can update the answer with query on the segment, and the same for the right option. If it is if it exists, then I can update the answer with max on the segment. Probably need to print some like exclamation point, right? And I need to write the query function. That should be it. Okay, I don't wanna figure out how to test it, I will just submit. Oh no, I need to figure out how to test it. Okay. The hidden permutation. That's fast. What happened? I didn't even read like the end line here, so it must have failed somewhere here. Oh. Okay. okay, 1 4 is 4. I can be sure about that part. Fuck 0. Oh, it should be 1. Okay. Let's try that again. 1 3. So our permutation is this, and the max of this is 2. This is 0. This is still 4, and this is still 2, and this is still 0. Is 2 correct? Yeah, I think 2 is correct. Okay. Somehow we figure out that the answer we're looking is 2. Okay, great. Okay, I fixed 2 bugs. Surely it works now, right? It looks like it does. At least on the sample. Okay, I can submit this. Okay, and we have 33 minutes for problem E. This is a run twice communication problem. Great. Plegma. What is with those names? Okay, there are 2 players. Actually, like I wanted to do screencast with commentary of this round because this is the first official round with communication problem on Cat. So I thought it will be maybe I can tell something interesting about this. There are 2 players, player A and player B. The jury will first interact with player A. After player A ends their interaction, the jury will interact with player B. Note that player A and player B may not directly pass information to each other. Both players are only able to set information or receive information from the jury, but they may agree on the strategies they will use to communicate. Yeah, because we are doing both player A and player B, and I presume. So they may agree on the strategies they will use to communicate. The jury has a binary grid G of n rows and n columns. Each cell of this grid has value either 0 or 1. Row 1 is the topmost row and column 1 is the leftmost column. The connectivity of this grid is defined as 1 if there is a path going left, right, up, or down, going through only cells with value 1, connecting each pair of cells I1, J1 and I2, J2 with ones. Okay, so like the connectivity of this grid is 1 if the cells with ones are connected by four directions. Note that moving diagonally is not allowed. It is guaranteed that there exists at least one cell with value of 1 in this grid. Okay, so the connectivity is 1 if it is connected. I'm assuming the connectivity is 0 if it is not connected, although they probably should have said it in this definition. Like if you define the connectivity like this, like they could have said it is the truth value of blah 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 connectivity. Connectivity is connectivity. But if you say that it is 1 if this happens, they should say it is 0 otherwise. Because what if it is 1 if this happens, and also 1 if this doesn't happen? Or it can be like 136 if it doesn't happen. I'm assuming it is 0, but it is not set in this definition, which is bad. Well, that is interesting. The jury first interacts with player A. The jury will give player A the grid G. After inspecting the grid, player A must determine two integers R and C and send them to the jury. At the start of player B's interaction, player B will receive the values of all cells in the R's row and all cells in the C's column from the jury. Note that player B is not given the values of R and C. Okay, so player A will get the whole grid, and then chooses a row and a column, and player B will receive like that row and that column, but not the values R and C. Player A wants to ensure player B can determine the connectivity of G. Your task is to act as both players and find a strategy so that player B is able to determine the connectivity correctly. Note that the communicator of this task is not adaptive. That is, the grid given to you on the first run will be the same as the grid used to evaluate the connectivity. Okay, cool. So, cool. Yeah, that sounds like a nice problem. At least, like, I don't know how to solve it right away, and like, it's interesting that, like, obviously player A can determine if the grid is connected or not. So they only need to send one bit of information, and they have like a lot of freedom. They have like n square possible responses, but the responses like are kind of encoded by the grid that is given to them, and that is the grid which connectivity you need to decide. And like, interesting. Sounds cool. So like, basically what that means is that like player A and player B, both of which are us, need to like determine a rule, like how by two like arrays of zeros and ones. Like, first of them is the row chosen, the second one is the column chosen. The player B must somehow determine like what to answer, 0 or 1. So basically we need to construct a binary function on those like row and column. So the function should take row and column and then output 0 or 1. What and like basically that function is what player B will do on the move. But then that function must be designed in a way that guarantees that if the grid is connected, player A can choose row and column such that like the function on them will give 1, and if the grid is disconnected, then the function on those row and column will return 0. Like, there can be a lot of functions, right? Well, exactly 2 to the power 2n. Yeah. Exactly 2 to the power 2n functions. And I'm assuming like a lot of them would work, but it is hard to understand like which ones will work. Like, technically what we can do is basically like choose a function at random, just like A and B will choose the same function at random somehow, like by set in the same rand seed, for example. And then A can just look at the connectivity, understand whether the correct answer is 0 or 1, then try all the options for row and column, calculate the function. If the function gives correct answer, then that's a good choice of row and column. Just send them to B. They will calculate the function and answer correctly. That's great, right? But we want to make sure that the function works. If it's just random, it probably works, but there might be with high probability any random function will work for any given input, but they need to figure out I don't know a way to make it work always. I mean, it can be randomized, I guess. I don't know. It kind of. Well, no, it cannot be randomized. It cannot be truly randomized, which means that they just choose one function. Okay. This is just rambling. I was not trying to solve the problem yet. I'm just rambling about the general how the problem looks. What you need to do in the problem. You need to construct that function, and it should be computable fast enough. But I guess we want to make sure that the function works always. What are the possible functions? I don't know. We can calculate the parity of number of ones in the two rows that are given to us. Will this always work? Is it true that you can always choose row and column with, for example, different parity if the answer is 1 and the same parity if the answer is 0? No, it is not true. There are some simple cases, for example, if our grid is just all ones, then we know that the answer is 1, but we also know that no matter which row and column player A choose, player B will always get the same input, right? This is some row, this is some column, what's the answer? We have to say yes. We have to say that the graph is connected because there is this grid which is connected, and player A do not have any choices here. They must send the row of all ones and the column of all ones. I don't think the same is true for when the answer is disconnected, because it is guaranteed that the grid will have at least one, and to be disconnected, I guess you need at least 2 ones, which should be in different connected components, and so there will be some degree of freedom. But not a lot. For example, we can have a case like this. We have one isolated one and everything else. So in the first row and last column we have just this one, everything else zeros. and everything else is ones, then it is disconnected. But what we can choose are like 0, 0, 1 or 1, 1, 1, 0 for the row, and well, basically the same choices for the column. I guess like if I put this one in like 1, 1, then it would be exactly the same. What are the choices? 0, 1, 1, 1 and 1, 0, 0, 0. So the player A will be able to choose one of those independently. That doesn't help me much. Like, there can be very different grids that are connected and very different grids that are disconnected. So like I need to come up with some like diverse enough function that if the grid is connected, I'm able to find a row and the column such that the value of that function is 1. And if grid is disconnected, I'm always able to find row and column and the answer is 0. This is actually a counterexample for parity, right? Like in the first grid, the parity is always 0, and in the second grid, the parity is also always 0. Like if you take just parity of the number of ones in the 2n bits that were given for the player B. Very cool. No idea how to do this. Maybe I'm missing something in the statement. There are some additional limitations. That's insane. I'm, I'm starting to think that you actually need something randomized. Because connectivity and how particular rows and columns look like has nothing in common. there are cases like so this is disconnected. This is connected. But like it has the same set of rows and columns. Like yeah, you can choose different rows and columns. So some choices of rows and columns, like with one missing cell, with 1 0, some of them should be 1 and others should be 0. So like you can't just look at the number of ones and zeros, you need to look at something else. But on the other hand, like you can have cases like when there is a big grid and there is like one cell that is good. This is connected. This is disconnected. You need to tell them apart somehow. You can also have like, I don't know, big grid that is almost full of ones, but like there are some cut out cells. So everything except those cells is good. This is connected. That's insane. Some randomized approach can be done, but like why is it good? Why is it to be honest, it doesn't even look like it should work. I have no idea. I have no idea what even one can try to do here. Did I understand the problem correctly? Well, I think so. It seems like a reasonable problem. Well, I'm very much interested in like looking forward to region what is a model solution. This seems incredible. It's like it is possible to solve this. Generally didn't find it hard. There's a lot of second division people who didn't find it hard. What? Okay, I guess I'm missing something obvious. Not obvious, but missing something. Okay, yeah, I'm interested to learn how to solve this. Well, my idea of making educational content on how to solve communication problems was cut short by my inability to solve communication problem in this contest. Well, that's great. Thanks for watching.